We are going to look at one more independent test, and this one is a two-sample proportions test. So here we are comparing two groups within the population, and we're looking at the percentage that have some kind of characteristic. And is there a difference between each group? So for example, let's look at the percentage of individuals who are divorced in Alberta versus the percentage who are divorced in British Columbia. Is there a difference? So in a two-sample proportions test, it's an independent sample, different people in each group. So there's the Alberta people and the BC people, and they're not the same people in the two different groups. And then we're looking at the proportion, so percentage divorced. And so we might have a null hypothesis that would say that the percentage divorced in Alberta is equal to the percentage divorced in BC. And the alternative would be they're not equal. You can also have a one-tailed test, so we could say the percentage of people in Alberta is greater than or equal to the percentage in BC who are divorced. That's the null. And then the alternative would be that Alberta is less than those in BC. Or alternatively, the null hypothesis could be that the percentage in Alberta is less than or equal to the percentage in BC, and the alternative hypothesis is that Alberta is greater than BC. So again, null hypothesis always contains 0. Alternative hypothesis is the one the researcher actually cares about or thinks is happening. So we can compare two proportions. And the test statistic for this is a z from the normal distribution. And so the test statistic is z equals, and then we have p hat, that's the sample proportion in sample 1, minus p hat, the sample proportion in sample 2, minus what we think that difference is. So if we are comparing, are they equal or not equal, then we would be subtracting 0 here. Then we divide by the square root of, and here we have to pool the proportions. So in the formula, you see a P sub C. That P sub C is the combined proportions. So we said, well, what if these two groups were all just one big group? So let's add the number of people who are divorced in Alberta and BC and divide by the overall combined sample size. So that's what you're getting on the bottom is the pooling of the proportions to help determine that standard error. All right, the assumptions for a two-sample proportions test are that we have a random sample. Remember, all hypotheses assume random sampling. And then here, because we're dealing with a proportion, divorced or not, we have a success or failure, two possible outcomes. It's a binomial distribution. We are assuming that we have independent samples. The people in BC are not the people in Alberta, and that we have sufficiently large sample sizes to take that binomial distribution and make the sampling distribution a normal distribution. Well, how do you get big enough? You take the number in the sample times the probability of, in this case, divorce. Is that greater than 10? And so I'm just going to zoom in a bit so you can see a little bit clearer. But what you do is you take the combined proportion times the sample size in group 1 and the combined proportion times the sample size in 2. That's what has to be greater than 10. And then the chance of failure, 1 minus the combined proportion times the sample size, must also be greater than 10. So this is our check to make sure the sample size is big enough in order for our binomial distribution to have a sampling distribution that is normal, which allows us to use our z-scores. Okay, all right, let's take just one more. I guess we've been talking about it. Let's zoom out just a little bit here. All hypothesis tests have a corresponding confidence interval because you're rearranging the test statistic. So here, solving for P1 minus P2, rearranging that test statistic, you can get your upper and lower bounds for your confidence intervals. All right, let's look at this particular problem here. Two different sides are being considered for a daycare center, one on the south side of town and one on the east side of town. The decision where to locate the daycare center depends in part on how many mothers work and have children under 5. A sample of 200 families on the south side of town revealed that 88 working mothers have children under 5. So our p hat for, what is this, the south side, is going to be 88 divided by 200. A sample of 150 families on the east side, so p hat east, is going to be 57 out of 150 have children under 5 and mothers who work. Can we conclude that in the population a larger proportion of mothers on the south side work than on the east side? Use a significance level of 0.05. N south is 200, N east is 150. Okay, let's start. Null and alternative hypothesis. The alternative hypothesis, can we conclude that in the population a larger proportion, so P is greater for south than for east? And to rearrange that, P south minus P east is greater than 0, which means the null hypothesis is P south minus P east is less than or equal to 0. Our alpha here is 0.05. Okay, and we need a decision rule. So here we have a Z distribution. Our alternative is greater than, so we are on this end. 0.05 is the space here. And we then have our Z alpha, and we would then reject H naught if our test statistic is greater than our critical value or our p-value is less than alpha. All right, in terms of steps, and I think I might have done this in some previous videos too, don't forget you need to mention what is the test statistic. Here we're doing a 2-sample proportions test. What are the assumptions for that 2-sample proportions test? The assumptions are random sampling, independent sample, binomial distribution, and that n1 times the combined proportion is more than 10, n2 times the combined proportion is more than 10, n1 times 1 minus the combined proportion is more than 10, and 2 times 1 minus the combined proportion is more than 10. So big enough sample size for a binomial to become a normal sampling distribution. All right, so given all that, let's do the test. All right, to do this in Excel, well, the challenge we have in Excel is that in our data analysis tool pack, we have t-tests for 2-sample, equal variance, unequal variance, and paired. Paired we're going to do in our next one, but these are all about means. They're not about proportions. And if we look here, there's the F-test, the 2-sample for variance that we talked about before in terms of testing whether the variability is equal. The variance is equal, but you'll notice there's really nothing in here about proportions. So that means that we're going to have to do it by hand. So what do we need? We need a critical value and we need a test statistic. Okay. Our critical value is going to be coming from that inverse normal, which I can never remember what the actual command is, equals norm inverse. And you want the one that is based on the standard normal distribution because you don't have a mean and standard deviation to give it, so we just want to give it a probability. What probability do we give it? Well, we want 0.05 to the right, which is 0.95 to the left. 0.95 to the left. Okay, now we need a test statistic, which brings us back to our test statistic here. So let's do it in pieces. We'll start with pooling the proportions, x1 plus x2 divided by n1 plus n2. And to do this, let's see. Got to be able to see it all at the same time. Okay. So x1, so we'll call this PC. Okay, so we have x1, which is our 88, plus we have x2, which is 57. So this is adding up all of the people who are working age mothers who have children under 5 in both samples. And we're dividing by the 200 sample in group 1 and the 150 in group 2. So our combined proportion is 0.41. If we had one big sample of 350 people, then it would have a 41% proportion in terms of the percentage working mothers with children under 5. All right, so that gave us this PC here, x1 plus x2 over n1 plus n2. Now let's do the rest of our test statistic. So we're going to do p hat, combine the number we just got, times 1 minus p hat combined, divided by n1. Okay, so let's bring this back, and let's pull this lower. Okay, all right, so let's do this in chunks. Equals p combined times 1 minus p combined. Times 1 minus, there we go. Okay, so what I've done is just this piece right here. And I've done it separately so that I can do, okay, take this number and divide by the sample size for the first group, which was 200. And then I'm going to do it for the second group. So I'm going to take this number divided by 150. Okay. So now what I have is these two bottom pieces here. So I'm going to then do equals square root, and I'm going to add those two together. So the bottom here, the standard error, is going to be 0.05. The top of the test statistic is going to be the difference between our two proportions and our samples. So P south and P east. And P south is 88 divided by 200 equals 88 divided by 200. And this one is 57 divided by 150. Okay. So the difference between south and east, our estimates were south minus east. So we do south our hypotheses were south minus east. And we were hypothesizing that the difference was different from 0. So we would take this 0.06 and subtract 0 from it. So our test statistic is this number, minus 0, divided by, and then we have our, just make sure here, that's our bottom of the formula. That's the square root here. So we end up with a test statistic of 1.13. All right, the critical value was 1.64. So we go back, our alpha was 0.05, so this is 1.64, and our test statistic is 1.13, which then puts us right here. So when we look at this, it says reject the null hypothesis if the test statistic is greater than the critical value. It is not greater than the critical value, so we fail to reject the null hypothesis. And it could be that the proportion, the percentage of women, working women with children under 5 is the same in the South and the East. So it's possible they're the same, or that we don't have a big enough sample size, or our methods couldn't detect the difference if there is a difference there. To do this in Python, so that we just did by hand in Excel. To do this in Python, just real quick, if you want to work along with us in Python, go to drstephpowers.github.io/BIA, scroll down to the bottom. We're doing hypothesis tests. You want to open in Google Colab. Once you do that, make sure you are logged into your Google Drive and that you save a copy so that you can edit and run the code. We are working down here towards the bottom of the sheet, so make sure you import pandas as PD and NumPy is NP because we're going to need that one in just a moment. Scroll down. We are doing right now two sample proportions tests. And to do our two sample proportions tests, we're going to use a package called statsmodels.stats.proportion. We're going to call it prop for short. So we're going to import statsmodels.stats.proportions, call it prop. This is the same package you used before when you did a one sample proportions test. The difference is that we are going to put in multiple proportions into the test. So to do that, we need to use that NumPy package, which we called as NP, to turn this information into an array. So this test is expecting this data in a certain format, so we got to make sure it's in that format. So we're going to call it counts, and that's going to be the number of working mothers with children under 5. In the first group, that was 88. In the second group, it was 57. So we'll do np.array, and then a soft bracket, and then a hard bracket, and then our two numbers. The number of observations, that's our sample size for our two samples. We also need to convert into an array, so we'll use NumPy to convert into an array and use a soft brackets and then a hard brackets, and then we'll put in our 200 and our 150. So this is just giving it the observations and the counts so that it can calculate the proportions, but it just has to be formatted a certain way for it to work. Then what we do is we do prop.proportions _ z-test, because we're going to use that z-score, and we're going to pull the counts we just defined and the number of observations we just defined. The last piece is to specify whether it's a two-tailed test or a one-tailed test. And if we go back to our data, we have that our alternative hypothesis is that the south minus the east is greater than 0. And so because we are doing greater than, then the alternative is going to be larger. So just a reminder, some tests use greater, some tests use larger. They do have different terminology, so you just want to be careful. If you're getting weird errors, it could be that your alternative is incorrectly specified. Okay. All right, so we run this. What you get, the first number is the test statistic, and the second one is going to be your p-value. So here we're getting a test statistic of 1.127 and a p-value of 0.129. Okay. Notice here the test statistic we got was 1.12767, right? Man, they look familiar. And with this, it is giving us the p-value of 0.1297. So going back, we reject the null hypothesis if the test statistic is more than the critical value. Well, if you did this in Python, you didn't bother coming up with the critical value. You could find it, but why do you need to when you have the p-value? And the p-value we have is 0.12. It is not less than the alpha of 0.05, so we fail to reject the null hypothesis, and it is possible that these two groups have the same proportions, or our sample size is not big enough to detect the difference. So in this case, we can see with just 2 lines of code and the proper package, we are able to do that test. So less work than having to do it by hand in Excel.